Okay, so let me share my screen. All right, so let's start with some things in algebra. Okay, so this is what we'll do. I have prepared some short slides in order to teach. So slides will contain most of the basic stuff, proofs, etc. If it is not given properly anywhere, then it will be given in the slide. Otherwise, proofs I'll take it from other places. Okay, for example, this lecture notes I had shown you last time. Some proofs are there in these lecture notes, so I'll just mention which proposition, which proof you have to see, and that way. Okay. So each time for each file, I'll give a specific name. For example, this is lecture 2, but this is lecture 2 in that particular course or wherever I picked it from. So this is not the name of the file. The name of the file is what is here on the top, proofs1.pdf. Okay, and accordingly, I'll upload it on MS Teams. So let us start. So this unit is about fields and field extensions. So what is a field? Any commutative ring F with unity is called a field if for every non-zero element there is some other element B. For any non-zero element A, there is an element B such that AB equal to BA equal to 1, right? So multiplicative inverses exist. So this is just a quick recap of what we discussed last time. Okay. Right. And 1 will always denote the multiplicative identity, just like 0 will always denote the additive identity. Okay. So, right. This is something that we had not properly done last time. Let's do it properly. Okay. So the characteristic of every field is either 0 or prime. How do we prove that? Okay. So let F be a field. Now consider the ring homomorphisms little f from Z to F. Okay. Defined by f of k is equal to k times 1 for all integers k. Right. So this is a ring homomorphism that is easy to check. So it has a kernel and the kernel is an ideal of Z. Right? But every ideal of Z is of the form n times Z for some integer n. Right? So kernel f is of the form nz for some integer n. We can choose n to be greater than or equal to 0 because minus nz is nz itself. Right? So we know the first isomorphism theorem for rings, which says that since f is a homomorphism, Z mod kernel f is isomorphic to the image of f. Right? If the homomorphism is surjective, then we can say Z mod kernel is isomorphic to the field f itself, but that need not be true. In general, Z mod kernel is isomorphic to the image which is f of z. Right? But the kernel is nz, so f of z is actually isomorphic to Z mod nz. All right, so this much we have. Now, what do we have to prove? We will have to prove that the characteristic is either 0 or prime. So if the characteristic is already 0, then there is nothing to prove, right? So if characteristic is 0, then there is nothing to prove. So now let's suppose that characteristic is not 0. So the characteristic is positive, right? But f of z is sitting inside f, capital F, which is a field. So f of z is a subring of f. In fact, it is a subring of f where the multiplicative and additive identities are the same, right? But f is a field and therefore f is also an integral domain. So if f is an integral domain, then a subring of an integral domain with the same multiplicative and additive identities is again an integral domain. Right? Only the multiplicative additive identities have to match. So capital F is a field, so capital F is an integral domain, and therefore the image of f is also an integral domain. But image of f is isomorphic to Z mod nz, we just saw. Right? Therefore, Z mod nz is an integral domain. That much we conclude. Okay. But now Z mod NZ is a finite ring. It's a finite integral domain. And you should have seen this in class before, that every finite integral domain is a field. Have you seen this? It is actually easy to prove. Every finite integral domain is in fact a field. Therefore, Z mod NZ is a field. But we know that Z mod NZ is a field if and only if n is prime, right? So Z mod NZ is a field and therefore n is prime. So what have we shown? If characteristic f is positive, then n, which is the characteristic of P of f, is actually prime. Is that okay?
Yes.
All right. So that was the basic thing. Now let's go to the main objects that we will deal with in this course. These are called field extensions. Then there is a special case, algebraic extension, transcendental extension, etc. Okay. So before we begin, let's start with a simple notation. Start with a simple notation. If K and F are two fields such that F is contained in K. Okay, so F is the smaller field, K is the larger field. Then we say K, the larger field, is an extension of F, or it's an extension field. And F, the smaller field, is a base field. Okay, base field, extension field. Okay, so K lies above F. That is the idea. And we will denote this by K bar F. K slanted bar F, which means K is an extension of F, field extension of F, where F is the base field. So let K over F be a field extension and alpha be an element of K, the larger field in the extension field. And we say alpha is algebraic over the base field F. If there is a monic polynomial over the base field such that it evaluates to 0 at the point alpha. Okay, so alpha in the extension field is said to be algebraic over the base field F. If there is a monic polynomial over the base field F, let's call it little f, such that little f of alpha is equal to 0. And if no such polynomial exists, that is if alpha is not algebraic, then we say alpha is a transcendental element. Okay, transcendental over F. That is also important. Transcendental over F. All right. So what is an algebraic extension? Any field extension K over F such that every alpha in the extension field K is algebraic over the base field F. Any extension K over F such that every alpha in K is algebraic over F is said to be an algebraic extension. And if this is not true, then we say it's a transcendental extension, which means if the extension field has at least one transcendental element, then we say it's a transcendental extension. Every element in the extension field need not be transcendental. Even if there is one transcendental element, we'll say that it's a transcendental extension. If you want it to be an algebraic extension, every element has to be algebraic. So are the definitions clear? We did this last time. Just a recap. Yeah.
Yes.
Okay. So yeah, just give me 1 second. Right. So I hope this much is clear. So these are the very, very basic definitions. Okay, now we look at some examples. So last time I mentioned that have a look at some examples of algebraic elements, right? Let's look at some examples. Okay, let's start with the most basic, most trivial, the simplest example. Take a single field F, right? Then F over F is a trivial field extension. F is subset of F, right? So F lies above F. So for any alpha in F is now both the base field and the extension field. There is a monic polynomial x minus alpha such that its root is alpha. Right? This is very trivial. What is a polynomial over F such that it vanishes at the point alpha x minus alpha because alpha is an element of F itself. Right? So for every alpha in F, there is a monic polynomial x minus alpha over F's whose root is alpha. Therefore, F over F is an algebraic extension because every element alpha of F is algebraic over F itself. Right? Let's go to the first non-trivial example. So R over Q is a field extension. Right? Reals over rationals is a field extension. Now we know that square root 2 is real, but it is irrational. So it does not belong to rationals. Right? Square root 2 does not belong to Q. However, it's a root of a monic polynomial over Q. Consider the monic polynomial x squared minus 2. You see? Because basically what you're doing here is you have square root 2, you square it and you get 2, which is an integer. So you have squared it, right? In order to get integer. So you take x squared. Okay, that's the basic idea. So if you take the polynomial x squared minus 2, which is a monic polynomial, leading term has coefficient 1. This is a polynomial over qx. In fact, every coefficient is an integer. So this is a polynomial over the rationals, over qx, over q. And square root 2 is a root, clearly, because square root 2 square is 2, 2 minus 2 is. Therefore, square root 2 is algebraic over q. Sorry, this is a printing mistake. Okay. Square root 2 is algebraic over q. I'll make the correction. More generally, for any natural number n, any natural number or non-negative integer n, it is easy to check that in a very similar way. Square root n is algebraic over q. Okay. The number square root n will be algebraic over q. So if I give you a non-negative integer n, can you tell me what is a monic polynomial whose root is n? Sorry, whose root is square root n? What is the proof of this that square root n is algebraic over q? Just look at what we did for square root 2 and tell me what will be a monic polynomial for square root n. Hello. Yeah, give me some answer. What is a monic polynomial for square root n if square root n is algebraic over q?
X square minus n.
Yeah, simple, right? That is exactly what you did for square root 2. If you take the square of square root n, you get n. So you just have to square it. So x squared minus n and square root n will be a root of that polynomial. Right? All right. So these are simple examples. Slightly more complicated example. Now C over R is a field extension. Right? Complex numbers over the real numbers is a field extension because every real number is a complex number. Reals are contained in the complex numbers. Now Let us show that every complex number is in fact algebraic over the reals. Every complex number is algebraic over the reals. Okay. How do you do that? So let Z be any complex number a plus ib. I is the square root of minus 1. And then the complex conjugate Z bar is a minus ib. Right? So these are some standard identities about complex numbers that we know. Z times Z bar is a plus ib times a minus ib, that is equal to mod Z square, which turns out to be a square plus b square. Right? The magnitude of the complex number whole square. And Z plus Z bar will be just 2 times the real part, 2a. The plus b plus ib minus ib will cancel. Now do you see that Z times Z bar, a square plus b square, this is a real number. Similarly, Z plus Z bar, which is equal to 2a, this is also a real number because Z is equal to a plus ib. A and b are real numbers. Real and imaginary parts are real numbers. Correct? But these are two numbers, Z and Z bar, for which you know their sum and the product. Then you know this formula, right? If you are given any two numbers, then you can construct a polynomial whose roots are those two numbers in terms of the sum and product. Right? So the only monic polynomial with roots Z and Z bar is this x minus Z into x minus Z bar. Correct? Both have to be roots. So you have to take both factors. But this is, if you simplify, x squared minus Z plus Z bar times x plus ZZ bar. Right? X squared minus sum of roots times x plus product of roots. In fact, this is how you factorize a quadratic uh, polynomial. You are given a quadratic equation of this kind. You say that the sum of the roots is the second coefficient, product of roots is the third coefficient. Can you find out the two roots individually, and then that will be the factorization. We have done all this, right? So now here Z plus Z bar is 2a, and Z times Z bar is a square plus b square. So the monic polynomial with roots Z and Z bar, which is x minus Z times x minus Z bar, is in fact this polynomial x squared minus 2ax plus a squared plus b squared. But this is a polynomial over the reals. Correct? So you took some arbitrary complex number Z, and this is a monic polynomial over the reals such that Z is a root of this polynomial. So in fact, both the root, the number Z as well as its conjugate. So Z and Z bar are roots of the monic polynomial x squared minus 2ax plus a squared plus b squared, which is over the reals. Therefore, both Z and Z bar are algebraic over R. But Z was any arbitrary element, any arbitrary complex number. Therefore, the whole field C is algebraic over R, or C over R is an algebraic extension. Is this clear, everybody? Simple manipulation using complex numbers shows that C over R is algebraic. So just take a look at it for 1 minute or so and tell me if something is not clear. Very, very basic manipulation using complex numbers. That's all we have used here. Is that okay? See, further examples will get more and more complicated. So make sure that you understand this fully before you go ahead. Anything that is not clear, any doubt? You are completely clear about what is an algebraic element, what is a transcendental element, what is an algebraic extension, what is a transcendental extension, what is a monic polynomial.
Yes, sir.
Okay. So make sure that when you go back, you write these things down at least once so that you will not forget. You cannot simply learn by reading from a slide. That is not possible. You have to write notes on your own. Okay. So make notes for yourself. Write down the proofs. Only then will you remember. Okay. So now let's consider another simple example. It's slightly more complicated than the previous one. I am taking now a special set of numbers, which I denote as q adjoin I. Q square bracket I is the square root of -1. Q square bracket I, which is defined to be all numbers of the form a plus ib, where a and b are rationals. Okay, so this is not all complex numbers. These are all those complex numbers whose real part and imaginary part are both rationals. Okay, or you can call them rational complex numbers. So why is this interesting? Firstly, let me show that Q square bracket I is in fact a field. It is a subfield of C. Okay. Now this is clearly a commutative ring with unity. That is not a big problem to check. Okay. So it is a commutative ring with unity, and you can assume that all we need to now show is that every non-zero element has an inverse inside Q square bracket I. Right. So let's take some non-zero element z is equal to a plus ib in Q square bracket I. It is non-zero, therefore the magnitude mod z squared is equal to a square plus b square is positive, strictly greater than 0, because this is a non-zero number, right? Therefore, you can always take the reciprocal 1 by a square plus b square. That is the important thing. And a square plus b square, rational numbers, sorry, a and b rational, so a square plus b square is rational, therefore 1 by a square plus b square is also rational. Okay, that's why we are working with the rationals. So if you take 1 by z, this should be easy. This is just z bar by mod z square. Sorry, z bar by mod z square is actually 1. So 1 by z is z bar by mod z square. Right? So what is z bar? A minus ib. Mod z square is a square plus b square. Splitting this, you get real part a by a square plus b square minus I times imaginary part b by a square plus b square. Both a by a square plus b square and b by a square plus b square are rational numbers because a and b are rational. Therefore, 1 by z is an element in Q square bracket I. Therefore, Q square bracket I is closed under inverses for non-zero numbers. Okay. So Q square bracket I is a subfield of C. Why is this interesting? So do you see Q square bracket I is a set of all complex numbers whose real and imaginary parts are rationals. Okay. Earlier we saw that every complex number is algebraic over the reals. Now we'll show that every complex number with both real and imaginary parts rationals is actually algebraic over the rational numbers. Okay, when a and b are in reals, a plus ib is algebraic over reals. When a and b are both rationals, a plus ib is in fact algebraic over rationals. That is the meaning of this. Okay, so check that same argument as in example C. Take an element z equal to a plus ib where a and b are now rationals. Compute z times z bar, z plus z bar, and you get the same polynomial x square minus 2a times x plus a square plus b square. Exactly the same polynomial, but since a and b are rationals, the polynomial is now over the rationals. Therefore, this element is algebraic over rationals. And this is true for every element here. So q square bracket I over q is an algebraic extension. Okay, so check this. It's the same argument as before. Okay, same argument as we saw earlier. Okay, so this was another example. Now we have seen examples of algebraic elements. Let's look at examples of elements which are not algebraic or which are transcendental. Okay, so it's a very, very deep classical result that e and pi are both transcendental numbers over the rationals. Okay, you know that reals over rationals, R over Q is a field extension. E and pi are real numbers, but they are not rationals. They are irrational numbers. And in fact, they are not algebraic over Q, they are transcendental over Q, both of them. Okay, this is a very difficult, deep result. So this is not proven in our course. We will not prove this in our course. But we will instead take a strong theorem. a difficult theorem without proof. We'll assume it without proof and then quickly we can show that E and pi are transcendental as corollaries. Okay. So in particular, E and pi are transcendental. So there are elements in R which are not algebraic over Q. That is elements in R which are transcendental over Q. Therefore, R over Q is not an algebraic extension. It is a transcendental extension. Right. So now how do we prove that E and pi are transcendental? So there is a deep result which we will not get into. We will just assume that and then this will follow quickly. Okay. So what's that result? So we obtain these as corollaries of the following much stronger theorem. Okay. So this is called Lindemann's theorem. Okay. Lindemann's theorem says the following. If Z is a complex number that is algebraic over Q, then E raised to Z is transcendental over Q. All right, just stare at this theorem for a moment. All right. So think of it this way. Think of algebraic numbers. Think of an element algebraic over Q to be an easier element to calculate or easier element or less complicated element. But transcendental elements are elements which are not algebraic. They are not roots of any polynomial of any finite degree. So they are much more complicated, much more difficult numbers to compute or calculate. Okay, that is an intuitive difference between algebraic and transcendental numbers. Okay, so if Z is a complex number that is algebraic over Q, that is an easy number over Q. E raised to Z is in fact a difficult number. E raised to Z is transcendental over Q. It will not be an easy number to calculate. Is that much clear? Lindemann's theorem, what it says. When you exponentiate, when you take e raised to a given number, the easy number becomes difficult. It becomes hard. An algebraic number, when you exponentiate it, it becomes transcendental over the rationals. Is that all right?
Yes, sir.
Okay. So how does this prove that E and pi are transcendental? So can you just look at this statement and tell me how E is transcendental? What is a proof that E is transcendental using this theorem? It's very easy actually.
If we take Z equal to 1, then
Mhm.
E is transcendental over Q.
So when you take Z equal to 1, what happens?
Then according to this theorem, E is transcendental over Q.
But what is the condition that should be satisfied?
1 should belong to set of complex numbers.
And
Algebraic over Q.
so is 1 algebraic over Q? It's not just any complex number, no? Is 1 algebraic over Q? Can you give me a monic polynomial over the rational such that 1 is the root of that polynomial?
X minus 1.
Yeah, that is what we were seeing. Q over Q is an algebraic extension, trivially. So one is an element of Q, one is an integer, one is a rational number. So x minus 1 is the monic polynomial. Okay. So one is algebraic, therefore e raised to 1, which is e, is transcendental. That is exactly what I wanted to do. Since one is algebraic over Q, P at e, which is e raised to 1, this is transcendental over Q. Now, what about pi? Okay, so pi is a slightly more difficult proof, even after using Lindemann's theorem. So pay careful attention to this. This will be the last part of today's this lecture. Okay, it will take some 10-15 minutes to complete. Okay, so pay attention now. We will now show that pi is transcendental over Q by using Lindemann's theorem. Okay, right. So how do we show this? We'll actually go by contradiction. So suppose pi is algebraic. You see, algebraic and transcendental are opposite. If not algebraic, then transcendental. If not transcendental, then algebraic. Right? So suppose by contradiction, suppose pi is algebraic over Q. So there is a monic polynomial over Q such that pi vanishes. The polynomial vanishes at pi. Right? So let f1 of x, I'm just calling it f1 for a reason. We'll come to that later. Let f1 of x over the rationals be the monic polynomial, be a monic polynomial. This need not be unique in case. Be a monic polynomial such that f1 of pi is equal to 0. Why will you get such an f1? Because pi is algebraic. We are assuming that pi is algebraic. Okay. So there is such a polynomial. Let's call it f1. Now I'm going to move around with this polynomial. Okay. I'm going to define some other things using this polynomial f1. So let me define g of x, a new polynomial g of x, to be f1 of x times f1 of minus x. Okay. So pay attention to this. This is a trick that we sometimes use to create new polynomials from older ones. Okay. So f1 we already have. We now create the polynomial g. G is f1 of x times f1 of minus x. Okay. Now do you see both x and minus x are present as arguments? So if I say, sorry. So if I say g of minus x, g of minus x is just again f1 of minus x times f1 of x, which is g of x itself. So this polynomial g is in fact symmetric in this sense. G of x is equal to g of minus x. Right? Just by definition. Okay. Now what is special about such polynomials? Now this is something I want you to check on your own. Okay. So if there is a polynomial such that g of x, polynomial g such that g of x is equal to g of minus x, then it will have only monomials with even degree. All the monomials will have even degree. There will be no odd degree monomials in that polynomial. Okay. So if g is a polynomial such that g of x is equal to g of minus x, then g of x looks like this. Right? It is monic because f1 is monic. So f1 times f1 of minus x is g, which is again monic. So the leading term is some x raised to 2n, right? Even degree, x raised to 2n for some n. We don't know what it is, some n. Plus the lower order terms are again of the form x raised to 2i, right? So the degree is even. Okay. So g of x will have this form, some x raised to 2n plus summation I going from 0 to n minus 1, ai x raised to 2i. So the monomials appearing are just x raised to 0, x squared, x raised to 4, x raised to 6, x raised to 8, and so on up to x raised to 2n. Odd powers like x cube, x raised to 5, they will not occur because of this property. How do you check this? Go back and check this. Take a form for g of x. Let g of x be equal to b0 plus b1x plus b2x squared plus dot 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 plus some dk x raised to k. Then substitute this condition g of x is equal to g of minus x. You will see that the odd terms will cancel. Okay, the odd terms will cancel off, only the even terms will remain. Therefore, you get this. Okay, so you go back and check this. I have written it just like, go back and check that G will be of this form. Okay, now here's the thing. When only even degree monomials are present, every power is in fact divisible by 2. Correct? So in fact, every monomial is actually a power of x squared. This is x squared raised to n. This is x squared raised to I. That is the meaning of saying every power is even, right? Then every monomial is actually a power of x squared. Then what you can do, you can define a new polynomial. We'll call that f2 to be g of square root of x. You see why g of square root of x makes sense? Because g of x is a polynomial in x squared actually. G of x is a polynomial where the monomials are powers of x squared. So when you substitute square root x, it becomes square root x whole squared raised to some power, which is just x raised to some power. So square root x and the x squared part will cancel off. That is the idea. So you can define g of square root x when g is of this form. Okay, so let f2 of x be equal to g of square root of x, which is precisely this, the same set of coefficients 1 and ai's, but now instead of x raised to 2n, you have x raised to n. Instead of x raised to 2i, you have x raised to I. And once again, since G is monic, F2 is monic. Is this much clear to everybody? Any doubts up to this point? We have just done some manipulation with the polynomial F1. Is that all right? If you have a doubt,
Yes.
you ask. Okay. So F2 is again monic. F2 is G of square root x. Okay. So from F1 of x, we have come to F2 of x. What property does F2 satisfy? So note that F1 of pi was equal to 0. Okay. Now if I take f2 of pi squared, that will be equal to 0 because f2 of pi squared, you put x equal to pi squared in f2. But that is equal to g of square root of pi squared, which is g of pi. But g of pi, what is g of x? f1 of x times f1 of minus x. So g of pi is f1 of pi times f1 of minus pi. But f1 of pi is 0. Therefore, this is 0. So f2 of pi squared is 0. Okay, so what have we done here? What we have done is the following. There is an algebraic element. Therefore, there's a monic polynomial which vanishes at that point. Using that monic polynomial, we have constructed a new monic polynomial which vanishes at the square of that point. Therefore, the square of that element is also algebraic, right? This shows that pi square is algebraic because f2 vanishes at pi square and f2 is monic. Okay, and f2 is over the rationals because everywhere here we are not losing the rational property at all. Not even here when you take square root of x because the coefficients remain as they are. They were rational before, they are rational now. But now this is not enough. Okay, this was one step. We got a monic polynomial vanishing at pi. Using that, we got a monic polynomial vanishing at pi squared. We will repeat this again the same way, exactly the same thing for pi squared. So now we have a monic polynomial that vanishes at pi squared. We can use the same technique to get a monic polynomial that vanishes at pi raised to 4 square of pi squared, right? We are repeating the same thing for pi squared. So now let me show it quickly. Repeat the above step. How do we do that? Define h of x to be f2x times f2 minus x. Therefore, again, we'll have h of x is equal to h of minus x for the same reason. Then again, for the same reason, h of x will not have any odd degree monomials, only even degree monomials. So h of x will be equal to some x raised to 2k plus summation j going from 0 to k minus 1, some bj times x raised to 2j. Only even degree monomials are present. Okay, and the degree is 2k for some k. And h is monic because f2 is monic. We do the same thing now. Now we are looking for a polynomial that vanishes at pi raised to 4. So let's call that f4. Okay, so f4 of x is defined to be h of square root x. Now, same thing, the same idea. Therefore, the square terms will become normal terms. So this is equal to the square and square root will cancel. This is equal to x raised to k plus summation 0 to k minus 1 bj times x to the j. And this is a polynomial over the rationals because everywhere the coefficients were over the rationals. And f4 is also monic. Now what do we have? f4 at pi raised to 4 by definition. This is equal to h at square root of pi raised to 4, that is h at pi square. But h at pi square by definition is f2 of pi square times f2 of minus pi square. But f2 of pi square is 0. We have already proven it. Therefore, f4 at pi raised to 4 is equal to 0. Okay, so we have done this trick 2 times. We got a monic polynomial that vanishes at pi. Using that, we constructed a monic polynomial that vanishes at pi square. Using that same trick again, we constructed a monic polynomial that vanishes at pi raised to 4. Okay, so you can do this for squares of elements. But why is this so important? This is important because of the following property. Now, do you note this? The element I, square root of minus 1, this satisfies the property I square equal to minus 1, I cube equal to minus I raised to 4 is equal to 1. Right? The order of I is actually 4 in the multiplicative group. Multiplicative group of non-zero complex numbers. I raised to 4 is 1. So instead of pi raised to 4, if I take I times pi the whole raised to 4, this is I raised to 4, pi raised to 4, that's equal to pi raised to 4. I raised to 4 is just 1. Okay. Therefore, we can write f4 of I times pi the whole raised to 4 equal to 0, not just f4 of pi raised to 4. It's also true for I pi substituted at f4. Okay, so now let us take this to be our polynomial. So define a new polynomial p of x to be f4 of x raised to 4. Because we're substituting fourth power, right? So let's take f4 at x raised to 4 as the new polynomial. F was monic or f4 was monic, therefore p is monic. F4 is over the rationals, so p is over the rationals. Now what is p of I pi? Exactly equal to f4 of I pi raised to 4. But I pi raised to 4 is pi raised to 4. So this is equal to f4 at pi raised to 4. But pi raised to 4 is 0. So p of I pi is 0. Therefore, what have we proven? P of x is a monic polynomial over the rationals which vanishes at I pi. Therefore, I pi is algebraic over Q. Right? We started, so once again to recap, we started with pi being algebraic over Q. That was our assumption. If pi is algebraic over Q, pi square is algebraic over Q. Pi square is algebraic over Q, then pi raised to 4 is algebraic over Q. If pi raised to 4 is algebraic over Q with this polynomial, then since I raised to 4 is 1, we can substitute pi, we can replace pi raised to 4 by I pi raised to 4. And therefore we can show that in fact I pi is also algebraic over Q. Is this much clear up to this point? I just repeated the same thing for pi square and then came up to this point. Is this much clear?
Yes, sir.
Okay, I'm pausing in between so that you can ask doubts if you have. Okay, If there are doubts, you have to ask. Okay, so we did all this in order to prove this. If pi is algebraic over q, then I times pi is algebraic over q. This is what we proved so far. Now we can use Lindemann's theorem. Okay, since I pi is algebraic over q, I pi is a complex number. I pi is algebraic over q, therefore e raised to I pi is transcendental over q by Lindemann's theorem. Lindemann's theorem says, let's go back. Any complex number that is algebraic over q, when you take e raised to that complex number, it must be transcendental over q. Right? So pi is algebraic, therefore I pi is algebraic, therefore e raised to I pi is transcendental by Lindemann's theorem. But e raised to I pi, we already know e raised to I pi is -1 by Euler's identity. Right? E raised to I pi plus 1 is equal to 0. That is the equation, right? Euler's identity, it is called. Correct? You can also use the formula e raised to I pi is cos pi plus I sin pi. Therefore, it's equal to -1. Right? So how can this be transcendental? E raised to I pi is -1. It's a rational number. It's an integer. It's a rational number. So it is in fact algebraic over Q. It is not transcendental. So this is a contradiction. Why did we get a contradiction? Because we assumed something wrong. We assumed that pi is algebraic. Therefore, we get a contradiction. Thus, pi is not algebraic over Q. Pi is transcendental over Q. That is the proof. Proof by contradiction. Is that clear, everyone?
Yes, sir.
Okay, so we just go through this construction once again. This is nothing special about pi. In fact, you can take any real number and show that if it is algebraic, then I times that real number is again algebraic by repeating the same construction. Okay, sometime I'll give you a tutorial and I'll ask you to solve this on your own, but it is basically the same construction. In case of pi, we can do this and then apply Lindemann's theorem and then get this contradiction. Therefore, we can show that pi is transcendental over Q. So I'll stop here. In fact, I wanted to do more. There are other things also in the slides. So, okay. Shall we do this? We are meeting again at 4:30, right? Shall I continue algebra itself at 4:30? We will do Python tomorrow.
Yes, sir.
Okay, so don't use the Python link in the evening. Use the algebra link itself. Okay, I'll also post an announcement in the WhatsApp group. So at 4:30 we will meet, not for Python, for algebra itself. We will continue this with some more examples and some results. Okay, so let us stop here.
Sir, can you please send these slides in MS Teams?
I'll send. So I will, there are some typos, no, in between. So let us complete this in the evening. I'll send after the evening lecture.
Okay, sir.
Okay.